we will discuss another problem to implement a Boolean functions of 4 variables given in the min terms forms, that means in the SOP forms, using 8:1 multiplexer. And we have seen in the 16:1 multiplexer, as we discussed earlier, that this is the truth table. This is the truth table of the Boolean functions. It is given here, and that truth table should be realized now with the 8:1 multiplexer. Here we'll adopt a slight different method to realize that. Here there are 4 variables. We will, similar to the entered variable map, will reduce one variable, because 8:1 multiplexer has 3 select lines. Therefore, if we are able to reduce one variable, then this truth table can be realized with the help of a 8:1 multiplexer. Therefore, it is just a slightly different approach we'll do. Therefore, it is similar to entered variable method, and that we're going to discuss. And you can see here, in similar to the entered variable method, as A, B, C, A equal to 0, B equal to 0, C equal to 0, and A equal to 0, B equal to 0, C equal to 0. And in that case, these are the 2 cases. You can see the Y is taking exactly similar to D. Therefore, if we eliminate, we can write Y as D in this case. Therefore, we are constructing another type of a truth table where the things will be more clear. Not in this type, 4 will be clear. Here we are showing that ABC variation is from 0, 0 to 1, 1, 1. There are 8 variation, and in this another 2 rows we are showing D0 and D1. In this case, you can see that when the values are 0, 0, 0, 0, 0, 0, D equal to also 0, output is 0. When 0, 0, 0 and 1, output is 1. We are putting here. Therefore, you can say that this is the for 0. This is decimal. I am talking about the decimal. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And then we just, what are the min terms are present? What are the min terms are present? Only I am talking about the subscript of the min terms. What are the min terms are present, and subscript of the, whatever I say, this is the subscript of the min terms. If the present, then we are putting 1. 1 is present, 1, 2, 2, 5, 5, 6, 6, 9, this is 9, then 12 and 13. And then we constructed this one. We constructed this. This is the truth table, which is in the similar this truth table. I just show you that why it is very similar. Here we have given the D in the same line, but here we are not giving the D in the same line. Here we have made D0 and D1. As a result, what is happening here? It is equal to, here you can see you can replace D, and here output you can write as D. And in this truth table, the benefit is that you can, comparison is very, very easy. Therefore, when 0, 0, 0, 0, A equal to 0, B equal to 0, C equal to 0, D equal to 0, your output is equal to 0. When A equal to 0, B equal to 0, C equal to 0, and D equal to 1, output is 1. You can see that very easily. You can see that these are very similar, D0 and D1. It is same as that of the D. Therefore, output is D. Here is output is D. Whatever I said here, the output is D. Here it is very easily visible that these outputs are same as D. In this case, you can see very easily, you can visualize that outputs are when A equal to 0, B equal to 0, and C equal to 1, and you can see here you can see A equal to 0, A equal to 0, B equal to 0, and 1, C equal to 1, and A equal to 0, B equal to C equal. You can compare these two. You can see these are the complement of D. Here it is very easily in this table. It's very easily visible. It is D0 here 1, D1 here it is 0. Therefore, we are putting output is D bar. Very easily it is visible. Therefore, we just change the this two truth table, whatever this truth table and this truth table are similar truth table. Here only difference is that this truth table, where I have to put in the simplified form, and where we're replacing the sum of the y, and the output we are replacing D or D bar. That where I have to put D and D bar, this is very easily you can, wherever it appears same as this, therefore we are putting D, and where it is a complement we are putting D bar. And that way we constructed the table, and we know that very well that the input to that multiplexer it should be whatever we are getting here D. D naught we are assigning D, D bar we are assigning D bar. Therefore D2 we are assigning D, and D3 we are assigning D bar, and D4 we are similarly whatever we are getting, and we are assigning to from D naught to D7. As in the case of a 16:1 multiplexer, we are assigning the serially we are assigning to D0 to D7. Now, if we come to that, if we come to that construction, if we come to that circuit diagram of this, and that circuit diagram is this is the circuit diagram. This is the circuit diagram, very similar to that. Whatever we got, there are 4 variables, A, B, C. These are the select lines, and D is the variable what is similar to the entered variable map. We have given in the input side itself. D and D bar we have given in the, this is the D bar, is given in the input side itself, and therefore as in the case you can see that it is D1, D3 are to D bar. Therefore, D1 and D3 are connected to the D bar, and you can see here D0, D2, and D4. You can see D2, D4, and D0 are connected to D, and D6 is 1. D6 is 1 connected to VCC, which is 5 volt. DCC you can say is a 5 volt, and D7 equal to grounded. You can say 0 voltage because it is 0. In that way, if you can construct this truth table, then constructing that circuit diagram is according to the truth table only, and it is very simple. Where only the connections of D0 to D7, which one wire you have to connect. One, it can be a D, it can be D bar, and it can be a 0 voltage, or it can be a 5 voltage, that is VCC. Is it according to the this table only, and that is the designing of 8:1 multiplexer, where only three variables, 3 selects are available, but we are designing it and implementing for a 4 variable Boolean functions. Another thing I want to mention here, that just now I discussed about the designing of a 8:1 multiplexer where the 4 variables Boolean functions can be realized. But another way that I wanted to mention here, that we can make a 16:1 multiplexer with the help of a 8:1 multiplexer and 2:1 multiplexer. And if the 2:1 multiplexer is not available, we can implement the 2:1 multiplexer with the basic gate with the basic gate here, whatever I have shown here, and then this combination 8:1 multiplexer, 8:1 multiplexer, and 2:1 multiplexer, which I implemented here with the basic gates, and that combination is a 16:1 multiplexer. After designing that 16:1 multiplexer with the help of a 2 8:1 multiplexer, we can give according to the Boolean functions exactly the similar way like a 16:1 multiplexer, and I think it is also another way to design 8:1 multiplexer. But one thing is that in the earlier case we required only one 8:1 multiplexer and basic gates. Here we require two 8:1 multiplexer. Therefore, the earlier one obviously it will be preferable, but from the academic point of view, in my opinion, that both should be accepted because we are concerned with the knowledge in academics rather than any economic